Hello students, let's see the next topic, average life and relation with half-life. We have already seen the half-life, so now we will speak about this average life and the relation between them. See here, as we have discussed earlier, the disintegration is never a spontaneous, which means it may be a spontaneous or it may take more time to. So we cannot actually clearly identify when it is actually going to disintegrate, which means all the nuclei of radioactive sample what we have taken do not disintegrate at the same time. One nucleus may disintegrate right at the beginning and some other may disintegrate at the end of the process also. So the lifetime of the different nuclei will vary from 0 to infinity, and that lifetime whatever we are actually going to calculate is nothing but this average life. Okay, so the average time for which the nuclei of a radioactive sample exist is called mean life or average life of that sample whatever we have taken. Okay, it is equal to the ratio of combined age of all the nuclei to the total number of the nuclei present in the given sample, which means age refers to the sum of all the lives of the nuclei divided by total number of the nuclei, lifespan of all the individual nuclei divided by total number of the original nuclei, the mathematical representation of this. So the total lifetime of all the nuclei divided by the total number of original nuclei gives you the average life, because this alone tells you the ability of the nucleus to decay, and it will be very useful for us if we calculate the average life. Are you getting the point here? So now if you consider this, simply to say, or why the in a single line if you want to speak about the average life, radioactivity, first of all it is a totally depends on the chance, probability. Anyway at the end we will get that topic, we will have the formula. So it's just like a random probability, which means we cannot exactly identify which nuclei is going to disintegrate first of all the given sample. So it is just like a random, so the probability which is nothing but, so taking a chance. Okay, so now let's go for the calculation and we will see the actual formula for that. First of all, if we consider a radioactive sample, let's say suppose it contains N0 nuclei at time t equal to 0, imagine so. Okay, after time t this number reduces to n, that's obvious, isn't it or not, from N0 to n. Let us say in a time interval t to t plus dt, very small interval I am considering, number of nuclei that decayed in that particular small interval dt I am calling it as dn. Can I call? And the life of each of the dn nuclei can be approximately taken to t, almost all this dn nuclei almost you can consider that to be t, because dt interval is a very small interval. So we can call that the total life of all these dn nuclei is nothing but t into dn. Can I call? Isn't it or not? So now total life of all these N0 nuclei can be integrated with as integral over summation refers to, that's it, right, sigma which I have mentioned. So integral over 0 to N0 t dn, while the total number of original nuclei is nothing but N0. Are we getting the point here? Okay ma? Right. Now look here, but from the decay law we already have this formula that dn by dt equal to minus lambda n. Now from this dn equal to minus lambda n dt, and of course this negative sign indicates that as the time passes on, number of nuclei getting decayed will be obviously reduces. So that was the negative sign gives. So dn equal to minus lambda in the place of n, n0 e power minus lambda t. We have already seen this, right? So minus lambda n0 e power minus lambda t dt. Substitute this dn value in this expression. So now what happens to the integral? Tau equal to integral over 0 to infinity t lambda n0 e power minus lambda t dt by n0. You can ask me that, sir, earlier you have represented the limit to be in the terms of number of nuclei, but now what happened to this? Observe carefully. Now what is my variable? Here it is the variation with respect to the number of nuclei. So initially it was 0, later on the maximum value is n0, total disintegration was, while here check this carefully with respect to the time, right? So you can call like at t equal to 0, substituting the limits that alone, at t equal to 0, n equal to n0 initially, that's it, right? And when n becomes 0, t becomes infinite. That's it, right? So that's what the reason what I am calculating here. So at t equal to 0, n is nothing but n naught, total number of nuclei. But for the total disintegration, it takes infinite time, right? So that was infinite. So t lambda n naught e power minus lambda t dt by n naught. Are we clear with this? So we will be left over with lambda t e power minus lambda t dt. That's it, no? N naught cancels out. Now we will be left over with tau equal to integral over 0 to infinity t into e power minus lambda t dt. What is the format of this integral? Integral uv. Are we getting here? Now if we simplify this integral, I think I hope you are very familiar with this kind of integration, uv integral. Okay, or shall I solve? Okay, anyway, I'll solve this. So let's solve this integral. Okay, so here is the integration. Applying the integral uv formula. Look here, I'll solve this upon applying the limits properly with respect to this. Here I have solved all that integration, and my final answer I got it to be as tau equal to 1 by lambda. What this 1 by lambda represents? Reciprocal of decay constant. So average life, whatever we got, or the mean life we can call, of a radioactive sample is equal to reciprocal of decay constant. That's it, right? We got tau equal to 1 by lambda. Now here we can have a relation with respect to the half life. Already we know that half life is nothing but 0.693 by lambda. Do you remember, right? And now we got tau equal to 1 by lambda. So in the place of that I can substitute, no? What I can get? Half life t equal to 0.693 tau, isn't it or not? If I substitute that. So let me substitute, and we can see the relation too. Okay, let's see that. Let's see the relation here. So we know that already half life t half equal to 0.693 by lambda, and just now we calculated that tau equal to mean life is nothing but 1 by lambda. In the place of lambda I can substitute 1 by tau, right? So upon substitution my final answer is t equal to 0.693 into tau, or tau equal to t by 0.693. Either is true, no problem in that. Now look here, as we know this relation n equal to n naught e power minus lambda t, nuclei at any instant, which we can calculate, and at that point if t equal to tau, in the place of time decay, time taken for that, that was tau. If I substitute n equal to, I got n naught e power minus lambda tau. So n naught e power, in the place of lambda I can substitute 1 by tau. So 1 by tau, tau cancels out, I will be left over with minus n. E power minus n is nothing but 1 by e. So n naught by e. Anyway, e value we know, if we substitute that, it is 0.37 n naught, or 37% of n naught. What we can say for this? Average life period of a radioactive sample can also be defined as tau. That's it, right? Can also be defined as I have substituted in this, so that's why I am defining this in also other way. The time interval during which 63% of sample decays or sample reduces to 37% of its original amount. Either is true. So 37% of n naught original amount, right? So the time in which the sample reduces to 37% of original amount. 37% of original amount is called average life, or you can call it as mean life. Either is true. We can we write down this? Okay, ma? Right. And you can also mention this this particular t equal to 0.693 beta, as I told you. So can we write down this t equal to tau equal to t by 0.693? Can I write down this? T by t half, which is nothing but half life by 0.693. And by the way, I forgot to mention, in many of the textbooks you can also get that half life will be represented with t half. Any of the notation is okay, no problem in that. Okay, just the symbolic notation alone. So t half by 0.693, can I write down like this? And 1 by 0.693 is almost 1.414. You can write 1.44. It was nearly 1.44 into t half or half life. Either way, 1.44 into t half. You can write down like this also, the alternate forms of mean life or average life. Are we clear with this? Right. Now let's see the next topic, determination of decay constant and half life graphically. Do you remember the three graphs what we have seen in the early and the beginning? So now I am going to consider that graph, and from there we can calculate the decay constant and as well as half life. Okay, let's see how we can calculate. This is the graph that which we are actually speaking about. If I consider time along x axis and log of n value, ln of value along the y axis, look here, maximum value, and it will keep on decreases. So this negative slope, right? So now we are going to calculate for that. Suppose n naught and n respectively are the number of atoms present undecayed initially and after a time t. Undecayed, which means initially, and after a time t it became n. And we have that relation, right? N equal to n naught e power minus lambda t. Apply log on both sides, log to the base e. So log n to the base e equal to log n naught a base e. Of course, it is in the format of log of ab. So log a minus log a plus log b. So which will be nothing but of this. Anyway, we have this exponential, right? So that was. Now I am going to convert this natural logarithm to the base 10. So I have to multiply with 2.303. So log n to the base 10 log n to the base 10 equal to log n naught base 10 minus lambda t by 2.303. That's it, right? If I multiply with that and if I take out common, that was. So now log n to the base 10 equal to minus lambda by 2.303 into t plus log n naught to the base 10. Now slope, which can be given as tan theta. That's it, right? Obviously, minus, if you compare this equation, y equal to mx plus c. So from that I can write down minus lambda by 2.303 is the slope here. That's it now. Mx plus c. X along we have taken, m in the place of m I have this negative value, minus minus cancels out, negative slope, right? So lambda equal to 2.303 into tan theta. Now I got the decay constant, right? Now let's calculate the half life. Okay, let's see here. The half life can be given as 2.303 into log 2 to the base 10. Actually you are very familiar with that t half equal to 0.693 by lambda. And can I write down like this? In the expression we have already mentioned this, right? ln2 by lambda. So in the place of ln2 natural logarithm, I am converting that into the base 10 logarithm. Now do you understand why I am considering this? So will be very easy for us. So 2.303 into log 2 to the base 10 whole divided by lambda, and lambda just now we have calculated, it was 2.303 into tan theta. 2.303 will cancel out, you will be left over with log 2 to the base 10 whole divided by tan theta. 1 by tan theta is cot theta. So the half life can be given as log 2 to the base 10 cot theta. So from the graph we can calculate like this. Log 2 to the base 10 is a constant value, 0.3013. So from that we can calculate this. Are we clear with this? Now let's apply the concept of probability for the case of nucleus disintegration and all, because as I told you already, it is a chance. We cannot actually speak at what which nucleus is going to decay first or which is going to be. So if we apply that concept here in a radioactive sample, when we apply probability, the probability survival of nucleus after time, first one, the probability survival of nucleus which is nothing but at after time t, which are actually undecayed, okay, after t second, which we can write it as, I am calling it as survival rate. So ps is nothing but n by n naught, which is e power minus lambda t. We can call this nothing new, n equal to n naught e power minus lambda t, we know that, right? So this ratio will gives us the probability survival of nucleus after t second, right? As you know very well, the probability will be always equal to 1, either positive or negative, yes or no, it can be head or tail, so like that. So the second condition is the probability of nucleus to disintegrate in time t. To disintegrate, I can write it as PD. I am writing it as the total probability will be equal to 1. So either it can survive or it can disintegrate. Both will combine, will gives you unity. So it can write it as 1 minus PS, the same result, right? So which is nothing but 1 minus e power minus lambda t. Are you getting the point here? A very rare situation you can you will get this kind of the problems. So just keep in mind, we can apply the probability here too. Are we Clear with this? Okay ma? Right. Let's see the next topic. Artificial transmutation of elements. So the actual use of this artificial transmutation of elements is, as I told you already, radioactivity can occur naturally. I told you the spontaneous disintegration of unstable nuclei by emitting out alpha, beta, gamma rays naturally at that topic, and that particular topic I told you naturally. So artificially also we can make that particular nuclei to go. So you can ask me, sir, you told that we cannot make any particular particle to go, but we can create that environment, but we can't make it to go. So okay, so by trial and error of many kinds of the projectiles by using, we can initiate the process, but we cannot make it to undergo further decay. That was it means. So artificial transmutation of elements refers to the conversion of one element into another by artificial means. Artificial means refers to using a very high energy particles and bombarding those high energy particles with some other stable nuclei or unstable nuclei will gives us or will yields a different kind of new variety of nuclei, and such a kind or such a process is nothing but we call it as artificial transmutation of elements. Rutherford worked on this kind of artificial transmutation of elements, and that led to the very actually great what do you call it as great work. That was actually his great work. And around after this, the discovery of artificial transmutation of elements, this leads to the discovery of the proton and neutron, of course by the respective scientists, and it helps to produce the radioisotopes also. Artificial transmutation, radioisotopes, which are nothing but the very which the isotopes are having a very short half lives, and are said to be called as radioisotopes. Very short, such are called said to be called as radioisotopes. Very specifically will be used for any other kind of the purposes alone. So production of radioisotopes is only used for having a greater application too. Later we have the applications, there we will discuss about that. Okay, and this artificial transmutation of elements is useful to produce transuranic elements also. So if you speak about the applications, the first one is it has medical applications. Radioisotopes I am speaking about. Radioisotopes uses or applications, you can call it as. The first one is medical. That means if you consider radiosodium, it is used to find in a particular given medicine, if that was given, circulatory disorders if the body is having, that can be identified by using radiosodium. Similarly, in treating like skin diseases, radiophosphorus will be used. Like in the treatment of thyroid glands, radioiodine is used. Like that we have many kind of cobalt in the treatment of cancer, and in treating anemia, which is nothing but anemia, which is iron is used for this anemia. So radio iron will be used for this. Okay, less amount of blood. And coming to the other application, it is used in geology. Second one is geology. Geology. In the case of geology, age of fossil fuels. Have you ever listened about carbon dating? You don't have this in syllabus, but very interesting one. Carbon dating. Age of fossil fuels can be identified by using this. So carbon isotope will be used for this, and age of rocks can be identified by using uranium, plumb, and all this can be used for this geology in the case of, and in the industry it can be used. Industry. In the case of industry, radioisotopes are used to find the wear and tear of machinery parts and to detect flaws in metal structures. Treatment of alloys, like in the case of quenching, annealing, hardening, in all this, if any treatment is needed, then it will be used. Selection of appropriate lubricants, for that also it will be used in industries, and in research it will be used. Research refers to which is in the case of nuclear disintegration of the elements, like in a very higher level of, so research purpose. research purpose it will be used. In food preservation it will be used, more important, food preservation. You can call exposing vegetables and other foodstuffs to radiations from radioisotopes, their shelf life can be increased. But of course that is not good for, but shelf life can be where very rare kind or such can be used in an emergency situation. Food preservation can also be used. Okay, and in agriculture also we can use. These are all high end but not in a regular we use. Where these are used in the sense, suppose if we use radiophosphorus for this, the uptake of phosphorus by plants can be studied. So using whether the plants are actually taking the phosphorus in a proper manner or not, that regular study of the uptake of the phosphorus of the plants can be studied. And minerals of which are transporting of the minerals inside the plants, in the plants, can be studied by using the radio sulfur, radio zinc, which is used to create new species and genetic mutation also, and irradiation to the gamma radiation which improves the yields. This is more important actually, which we have most of the this seeds manufacturing companies will follow this, but that doesn't give a proper yield actually. The genetic mutation and irradiating to the gamma rays will improve the yield. Under that, if that was not taken in a proper way, or if that irradiation was not taken in a proper manner, that leads to the failure of the crop too. Okay, and in chemistry also we can have that is used to study the mechanisms of many reactions, can be done by using this radioisotopes. So all these are the various kinds or various uses you can call of this radioisotopes. Keep them in mind, useful for your further purpose kind of. Okay.